in the last lecture, we discussed about angle sections or ISS angles. We discussed two numericals regarding. The first one was single angle section and the second one was double angle section. Today we will be seeing HSFG bolts and some more advanced problems regarding butt joints. So moving on to the question. Here the question is, determine bolt value of a 20 mm dia 8.8 grade, or you can say HSFG bolts, that is high strength friction grip bolts connecting two plates, and the thickness of both the plates are 12 mm and the width of plate is 200 mm. The grade of plate is given here as 410, that is normal conditions, and it is also said to design the joint if it is subjected to a design tensile load of 250 kN. As the load is given here as design, there is no need to multiply by 1.5. Clear? So the bolt diameter will be 20 as M20 bolts are given, and as per our understanding that we have seen table 19, the hole diameter will be 22. Now for HSFG bolts, FU will be always taking as 880 Newton per mm square. We have discussed it in the first introduction lecture. So if we discuss about HSFG bolts and the ordinary bolts that we discussed in the previous lectures, then the main difference here is that in the ordinary bolts we were calculating two types of capacities, that was shear capacity and bearing capacity, and out of this the smaller value will be taking as bolt value. Here in the case of HSFG bolts we will be calculating three capacities, that is the first one will be slip resistance, the second will be bearing resistance, and the third one will be tension resistance. And again the pedagogy will be the same, that we will be calculating these three values and the final answer will be the smaller of these three values. Clear? So moving or starting our sum, the first value that we will be calculating is the slip resistance, and for finding slip resistance you need to pause this video and move on to page number 76 of your IS code. So on your page number 76 you can see here that clause 10.4.3 is prescribed. It is the clause for finding slip resistance, or you can say slip capacity of bolt. This is specifically used only when HSFG bolts or 8.8 grade bolts are given. Okay? So in this case we need to find VDF. The equation will be VNSF upon gamma MF. Again gamma MF and gamma MB will be the same as we have discussed from page number 30 of your IS code. It will be 1.25. Now moving on to the value of moving on to the value of VNSF, the equation here as per our IS code is mu F Ne KH F0, that is capital F0, divided by gamma MF. Clear? So if we talk about VNSF, the terms or the parameters that we need to understand are, first is mu F, second is Ne, the third is KH, and the fourth is F0. Capital F stands for force, whereas small f stands for stress. Keep this in mind while solving the numerical. So the first thing we'll be discussing is mu F. Now mu F will be equal to 0.48. Now how this value came we will be discussing somewhat later on in this slide. Now first then we will be looking upon the value of Ne. N again is the number and E here is for shear planes. As we have discussed in the ordinary bolts, here the consideration will be the same. There we were discussing NN and NS. Here in terms of HSFG bolts we will be replacing it by Ne. The conditions are all the same, that number of shear planes associated with our connection, that is our lap joint. Clear? So in this case as two plates are given, so if we apply tension force on it, the number of shear plane will be 1. So here Ne equal to 1 is being taken. Now moving on to KH. KH, as you can see in our IS code, that KH, three values are prescribed for KH. The first value for KH is 1.0, the second value is 0.8, whereas the third value is 0.7. The first value, that is 1.0, is for clearance holes, as you can see in the IS codes. Clear? So for this semester or in this entire semester we will be dealing with only KH equal to 1.0. So in each and every sum regarding HSFG bolts you will be taking KH equal to 1.0. Now again coming back to mu F. Now how this mu F equal to 0.48 is being taken? For that you need to refer table 20 of your IS code. In this table, as you can see in the screen itself, the values are being prescribed. There are many values, and in this you can see that the second column describes the characteristic or the property of the material that was used. These properties or these characteristics are to be implied only when it is asked in question. Keep in mind. and up till now GTO has not asked anything regarding this table. So in this case I have taken the value as 0.48. As you can see in the IS code, it is for sand blasted furnace. Here I have taken the value 0.48. It is not compulsion to take 0.48. Now as per our code, you can say here that mu f equal to some equation is given, and in the last in bracket it is mentioned that mu f equal to 0.55. So if you want to write this mu f equal to 0.55, then also it is viable. It is nothing wrong in that. There will be no variation in the final answer. So either you can take mu f equal to 0.55 directly, or you can use the table 20 that we have seen. Yeah. So these were mu f, kh and Ne. Now moving on to the last term, that is F0. Now capital F is our force, and as you can see in the IS code again, the equation for it is A and B into small f0. Clear? And A and B is again the area of, or the net area of bolts. Clear? As we have discussed it earlier also, the threaded region, the area of bolt at the threaded region, which will be 0.78 into pi by 4 d square. So here the value comes out to be 245. Now substituting in the equation, we get the value as to be 0.7 into 800 into 245, and the final answer is something 137 kilonewton round. So substituting everything in the equation for VDBF, we get the final answer as 52.68 kilonewton. Yeah, so this is our slip resistance or the slip capacity of bolt. Moving on to the bearing capacity of bolt. The bearing capacity can be found from the same equation that we were using in ordinary bolts. Just to keep in mind here, if we need to find KB, then we can use these 4 equations as prescribed in our code, or if we don't want to find KB, then for this particular sums, that is regarding HSFG bolts, you can write directly the KB value as to be 1. It will be of no issue. You can either write directly KB equal to 1, or if you need to find the value of KB as per these 4 equations, it will be good. So solving it, we get answer 196.8 kilonewton. Now keep in mind in this case that whenever we are dealing with bearing capacity, Fu will be considered the smaller value. Keep in mind, Fu will be the smaller value of both the materials. Here the material being used is first is of our HSFG grade bolt, and the second is of plate, that is plate is of grade 410. So the Fu of plate here is 410, whereas the Fu of bolt here is 880. Yes, this is a typical sum. In general considerations, you will be asked 4.6 grade bolts. So for that, there is no need to worry about. But whenever a special category is been asked, or it is asked rather than 4.6 grade bolts, then you need to keep this in mind that bearing capacity equation, Fu will be taken as the smaller value of both the materials. Now for, as you can see here, that Fu for bolts is 880 and Fu for plates is 410. The smaller value of this both will be obviously 410. So replacing 410 as in the case here for Fu, you will get this final answer as 196.80. This was our second equation for bearing capacity. Moving on to the third equation. Third thing we need to find is the tension resistance or tension capacity. Clear? So again, briefing it out, the first was slip resistance, the second was our bearing capacity or the bearing resistance, and the third will be tension resistance. Out of these 3, the simplest is tension resistance. As you can see from clause number 10.4.5, the equation for it is TDF, and TDF is equal to 0.9 FUB An upon gamma MF. But in code, if you see, there is some relation given between these equations, that 0.9 FUB An upon gamma MB is less than some equation part is being given. So that case, or that is to be applied only when we are actually designing the connection. We are not designing the connection here, we are just finding the capacity. So if the capacity was given and you need to find something pertaining to design of bolts, so bolts are to be identified, or we need to find the design of bolt, then and then only we will be using this relation. For solving the analysis portion, you can use the LHS value of it. So the final answer will be, in this case, 0.9 FU, the FUB, that is for bolt. For HSFG it is 800. An, again An will be the area or the net area in the threaded region, which comes out to be 0.78 pi by 4 d square, and divided by gamma MF. gamma mf will be 1.25. So solving this, we get answer 141.12 kilonewton. So taking a summary of all the three loads that we have calculated, the first was VDBF, that was our slip resistance. The second was bearing capacity or the bearing resistance, and the third was tension resistance. So out of these three values, the smaller value will be of shear or for slip resistance. So this will be our bolt value, and here to find number of bolts, the equation will be again same, that bolt value, or to find the number of bolts, the equation will be total load divided by bolt value. Total load as it is given in equation as 250, and we have calculated bolt value to be 52.68. So solving it, if we get an answer, the total number of bolts we are getting it 4.74. So rounding it off, the final answer will be 5. And moving on to the figure that we need to draw. Here two plates are being prescribed. So the hidden line here, it shows that the bottom plate is overlapping. Clear? So the top plate and bottom plate both are being overlapped, and the dimension, as you can see, the width will be seen only in the plan section, plan view that we have discussed, or we will be discussing in here. And the total number of holes or bolts are to be placed will be 5 as per our final answer. And in the figure itself, you need to mention the values of E and P, that is of edge distance and pitch distance. Clear? So E will be equal to 1.7 D0 and P will be equal to 2.5 D. Okay? So either you can solve it directly from the KB equation, or if you have not solved the KB equation, then you need to find it again for the purpose of this figure reference. Clear? So this was our sum pertaining to our HSFG bolts. Again, keeping in mind, HSFG bolts are different as compared to ordinary bolts. Here we need to find three values. The first one being the slip resistance, the second one being the bearing resistance or the bearing capacity, which will be same, and the third is tension resistance. Out of these three, the smaller will be our bolt value. The rest procedure is same. So moving on to our next sum today. The question here is, two plates 18 mm and 10 mm thick are connected by a double cover butt joint. Keep in mind, we have discussed lap joint until now, and this will be our first and last sum regarding our butt joint. Clear? So using 8 mm thick cover plates. So the thickness of cover plate is mentioned here in question as 6 mm, and as in figure that we will be discussing later on, find the strength of M20 bolts of grade 4.6 and Fe410 plates are used. So here we need to find the strength of joint. And so what is different in this case, we will see later on. But moving on to the figure portion first. Two plates are given in the question, and as it is a butt joint, it will be placed side by side. It will be not overlapping each other. So these are our two plates having dimensions. The first plate is of 18 mm dia and the second plate is of 10 mm dia. It is connected by a double cover butt joint. That means two cover plates are being connected here of 6 mm thickness. The bolts are being already given in the question. That 6 numbers of bolts are used on both the planes, or both the plates. The number of bolts are being used as 6. But as you can see here in the figure itself, that the thickness of both the plates are not same. And if the thickness of both the plates are not same, then what will happen? The cover will be not stable and it will be not in equilibrium, so thereby the strength will be not proper and the failure will be done in this case, or we will be getting a failure in this case. So to avoid this, we will be providing a packing plate. We will be providing a packing plate to get a proper bond or to get a proper strength for this material. So now the thickness of packing plate is to be identified. So as the left plate was of 18 mm thickness, the right plate was of 10, that is 10 mm thickness. So the remaining portion will be of 8 mm thickness. So our packing plate will be of 8 mm thickness. Clear? So now moving on to our sum. The D and D0 will be identified from the question itself, D being our diameter of bolt and D0 being our diameter of hole. Now the thickness of packing plate is, as we've seen, 18 minus 10 equal to 8 mm. Why to find this? Because we'll be now moving over the new equation that we will be referring. So the equation here you can see from your IS code, page number 75. It is mentioned in clause number 10.3.3.3. Here you can see that the design shear capacity of bolts. keep in mind it will be only change, or the value will be only changing in the shear capacity, that is VDSB. It is not related anything to DPB. That is, in the case of bearing capacity, nothing will be changed. It will be same whether to provide packing plate or not. But if packing plates are provided, then we need to check the shear capacity of bolts, that is VDSB. And for that, you can see in the question it is given that, or in the equation it is given that the design shear capacity of bolts carrying shear through a packing plate in excess of 6 mm. So we need to find this beta pk equation only when the packing plate thickness is in excess of 6 mm. Here in our question, the packing plate thickness is 8 mm, so we will be solving this beta pk equation. The equation for beta pk, as you can see in the code, is 1 minus 0.0125 tpk, and tpk is thickness of packing plate. Clear? So solving it, we will be getting an answer that 0.9. Beta pk will be equal to 0.9. Now how to use it? This beta pk will be multiplied in VDSB. There is nothing more to do it. We need to find VDSB from the same method that we are using. So for finding VDSB, again you will be referring the same clause, that is 10.3.3. The equation will be VNSB equal to FU by root 3 NN ANB plus NS ASB. But keep in mind, here we are dealing with a double cover butt joint. Till now we were discussing lap joints. So the main difference between a lap joint and double cover butt joint is that in lap joint, whether it will be of single shear or double shear, we will be considering these values only in NN portion. Again, whether it is given as single shear or it is identified as single shear or double shear, we will be keeping the value 1 or 2 in the term NN itself in case of lap joints. But for butt joint, and specifically double cover butt joint, we will always keep one portion or one value in NS. Clear? So for a double cover butt joint, in each and every sum we will be keeping NN equal to 1 and NS equal to 1. Clear? So assuming NN equal to 1 and NS equal to 1 specifically for double cover butt joint, we get an answer 400 divided by root 3, that was our FU by root 3, and NN will be 1. Again A and B will be 0.78 into pi by 4 d square, plus now this time our second portion will be calculating. Till now we were keeping 0 in the second portion. Now it will be considered. So NS will be 1, and ASB, as we have seen earlier, ASB will be the area of bolt in shank, and as shank is not a threaded region, so the area will be directly pi by 4 d square, which comes out to be 314.15, and multiplying by beta pk. Don't forget here, as the packing plates are given in question, you need to identify first whether the packing plate is greater than 6 mm or not. If it was less than 6 mm or equal to 6 mm, we won't have identified or we won't have calculated beta pk. But if the packing plate thickness is greater than 6 mm, we always will be calculating beta pk and will be multiplying in the equation of VDSB. So beta pk or packing plate is only used up till VDSB. It is not used in VDPB. Clear? So solving it, we will get an answer. Shear capacity will be equal to 92.97 kilonewton. Clear? Now moving on to the bearing capacity of bolt. Again, it will be of same equation, 2.5 kb dt Fu. Moving on, we will be getting an answer 2.5.606. Here solving kb, we will be getting the smaller value of kb as 0.606. Here we don't need to write directly 1. Clear? In the last equation, or the last question was for HSFG bolts. So for HSFG bolts, you can write directly equal to 1 if you want. If you want to calculate in that portion also, it is well and good. But for ordinary bolts, you compulsory need to identify or calculate the value of kb. Yeah? So solving it, we get an answer 121.2 kilonewton. But here keep in mind again, in bearing capacity, Fu will be the smaller of both materials. As we are dealing with ordinary bolts now, and the plate is of 410, so both the values of Fu for bolt will be 400 and for plate will be 410. So the smaller of these two will be 400 Newton per mm square. So now we'll be finding VDPB, and the equation for VDPB will be VNPB upon gamma MB. So the final answer is 96.96 kilo Newton. Now taking a summary of all these things, the VDSB, there was shear capacity was 92.97 and the bearing capacity comes out to be 96.96. So out of these two, the smaller value will be 92.97, that will be our bolt value. But keep in mind here, we are not supposed to find the number of bolts, clear? So the next step won't be to find number of bolts, as the number of bolts are already given in the question. Now what to do? Now here in this case we need to find the strength of joint. We have already identified the bolt value, that means strength of one bolt. Bolt value will always be strength of one bolt. Now in the question it is given that total number of bolts are 6. Clear? In the question it's given that total number of bolts are 6. So the total strength of bolts will be this bolt value multiplied by 6. Keep in mind. Clear? Now we will be dealing with each plates. We won't be multiplying both the plates now, because we will be dealing with each plate, that is the joint itself. Clear? So here the design strength of bolt will be 6 into 92.97, that comes out to be 557.82. So this was our today's lecture. We are concluding our bolted connections here, and from the next lecture onwards we will be starting with our welded connections. Thank you.